moving on to another topic. Now that we were able to quantify the signal-to-noise ratio, now it's time to try to obtain the probability of error, or the beta rate of the system, which is a measure of the performance of the system. How well does the system perform? If the beta rate is very large, then there are many errors being received at the receiver, so it's not good performance. If we have a low number of errors, then that's obviously the ideal case that you want to be operating on. Okay, so let's see how this and so we're going to see how to calculate the probability of error, the relation between the beta rate and the signal-to-noise ratio. And these are the two main points on these slides that I have to show you now. Basically, for those who have already had fundamentals of telecommunications, I think this is not new. For the students from engineering physics, then I mean, these probabilities, and students in physics also had, I think they have a good background in probabilities. Still, the application of probabilities to telecommunications might be something perhaps new. And so I'm going to summarize some main points here. Again, we are assuming that the noise follows a Poisson distribution or a Gaussian. You're using a Gaussian approximation to model the noise. And we know that the Gaussian distribution is given by this equation here, if you remember. So is this equation here, where M is the mean value and sigma is the variance, or sigma squared is the variance and sigma the standard deviation of the distribution. And we know for the Gaussian distribution, only these two parameters are required to define fully the distribution, the mean value and the standard deviation. So at the receiver, what we have is the following. So basically, and I think is relatively forward to understand that we have this, remember that we defined the threshold level, if you remember, where at the decision time, the decision circuit decides whether a 0 or a 1 level is being received. Okay. And if this is what is shown here in this diagram, is the signal plus noise. This is the signal corresponding to a 0 level and the 1 level. And we have an average value for the 0 and for the 1, but around this average value, we have some variations around the mean value. Okay, but we know that if the noise follows a Gaussian distribution, we know that the distribution of noise, for example, around the 0 level, this is the mean value. So this will be the mean value, right? And we have a certain distribution of the noise around the mean value, which is given by the Gaussian distribution, as given by the equation in the slide above. Okay. The width of this curve is related to the variance of the noise corresponding to the 0 level. And so we're going to say that in general, the noise associated, or the variance of the noise associated with the zero level is different from the noise associated, or the amount of noise associated, or the variance of the noise associated with the one level can be different from the zero level, okay? And we can do exactly the same procedure for the one. So we have, when we are transmitting one level, and this corresponds to a certain mean value, which will be the mean value associated with the one level. And then we have a certain distribution of the noise around this mean value, okay? And we are going to say that the variance associated with the one level can be different from the variance of the noise at the zero level, which means that the amount of noise can actually be different from the one and the zero, okay? And this is the case for optical receiver, because we see that the quantum noise if you remember, we defined the quantum noise as 2 times electronic stars times the average current associated with the signal. And so this value takes, let's say, takes a value for the zero level and takes a different value for the one level. And for the one level, the signal is higher. If the signal is higher, then the quantum noise is higher. So in general, in the photodetector, unless thermal noise is dominant, in general, the noise associated with the one level is usually higher, or in general is higher than. So what I'm saying is that in an optical receiver, sigma 1 is usually higher than sigma 0, unless thermal noise is dominant. And so quantum noise can be neglected. In that case, they will be identical. Okay. And so for general case, we could say that optical receiver variance of the noise in the one level is higher, or in some limiting cases equal to the noise at the zero level. Okay. How can we now, and that's an interesting question, how can we now determine the probability of error? Does anyone wants to guess? And by the way, some important notation here, which is we're going to say that we're going to use this notation, probability. This is the probability density function, which is a Gaussian distribution. We're going to write P of y, which is the probability that a certain value is obtained. Sorry, given that a zero has been transmitted. Okay? This is known as the conditional probability. Sorry, conditional probability. Sorry about the letter. It's not easy to write. And the same for the one level, Py dash 1 will be the conditional probability, which means it's the probability of occurrence of a certain value at the receiver, given that the one has been transmitted. Okay? So how can we now calculate the probability of error? So what's the probability that the decision circuit, for example, when a 0 has been transmitted, a 1 has been detected? How can we calculate this, knowing if we know the conditional probabilities of 0 and 1? Does anyone want to make a guess? When is, if a 0 has been transmitted, sir, okay, and this is the mean value, when does an error is detected, or when is an error occurs at the receiver? Anyone?
An error will occur when the value that we get is above the threshold voltage.
Exactly, because the threshold voltage defines the level or the boundary, right? This is the boundary. Below is a 0, right? And above is a 1. And so if we transmit a 0, but at the decision time, if the detector measures a voltage which is above the threshold voltage, then that means that a 1 has been received, which corresponds to an error. And so the probability that a 0 is transmitted and a 1 has been received corresponds to taking the probability. So the probability that we receive the 1, but when a 0 has been transmitted, corresponds to probability density function, or conditional probability that a 0 has been transmitted, and corresponds to this region here, right? To this area around the curve, which gives all the possible values above the threshold voltage when a 0 has been transmitted, right? And so we need to take the integral from minus infinity to the threshold voltage, right? That's what you need to do. And in the similar way, for when 1 has been transmitted, okay, with a certain mean value, the error will correspond to this area around this curve, which gives all, when a 1 has been transmitted, but all possible values below the threshold voltage corresponds to a 0 being detected, which it is an error. And so we need, again, to take the integral, but now the limits are different. Okay, that's the only the different, given the conditional probability that the 1 has been transmitted. And this is summarized in the following slide. Okay. Actually, it's not here, but it's here. So if a bit 0 was sent, yes, assuming a bit 0 was sent, the probability that noise exceeds the threshold voltage, which corresponds to a 1, is taking the limits of the integration. So this is the probability, the conditional probability that a 0 has been transmitted. So the mean value corresponds to the mean value of 0, and a certain variance corresponds to the 0. And so, but the limits of integration is between the threshold voltage to infinity, where when a bit 1 is sent, the probability that the signal detected is below threshold. Since a 1 has been transmitted, we need to use the conditional probability associated with 1. And the limits of integration is from minus infinity to the threshold voltage. Okay. Now, just going back here to the some notation to understand what we are talking about. We're going to describe the bit 1 with a certain average, which I will call it B sub on, and the variance sub on, which is equivalent into this equation here. Sorry. So it will be equivalent of saying that this is B on, the average value, and this is, in this notation, is B off. And we will describe this, the variance is sigma square on, and this case sigma square off. So previously I was describing this as B0 with a 0 and a 1 index, but the notation I have here is off and on is equivalent. Okay, that's the notation I'm going to use now. Okay. So as I said, the level of noise associated with the on level is higher than off level due to shot noise in an optical system. So that's it. So, and how do we write the probability, the conditional probability that the 0 has been transmitted? So we know it's Gaussian distribution is 1 square root of 2 pi e to the minus. Then we have y minus the average value corresponding to the off level divided by, sorry, square divided by 2 times the variance of the off level. Okay, that's it. And the conditional probability associated with 1 is simply 1 over square root of 2 pi sigma, I think. Yeah, 2 pi sigma off here, square root 2 pi sigma on, e to the minus y minus b on square over 2 times sigma square on. So these are the expressions for the condition probabilities of 0, 1. So we need to replace these equations here. Okay. And just take the integrals with the defined limits to obtain the probability of error. Okay. Sorry, made a mistake. This is the same. Yeah, we need to do this and this one here to obtain the probability of error. Okay, that's it. And so we need to calculate this, except that these integrals, they don't have an analytical solution, but it can be defined in terms of the error function, okay, as we're going to see. And so if we know the probability associated with ones and the probability associated with the 0, or the on level and the off level, then the total probability of error is the combination of these two, given a certain distributions of ones and zeros. Okay, and so A here is the probability of zeros, and the B is the probability of occurrence of ones. So to do the calculations, we're going to simplify the analysis and assume that ones and zeros have equal probability, which means A and B have identical probabilities and equal to 0.5, 1/2. And so this equation in this case becomes simply multiplied by 1/2. As I said, these probabilities, which involves these integrals, can be calculated in terms of the error function or the complementary error function, where the complementary error function is 1 minus the error function of x, is the complementary error function, which are given by these probabilities are given by these functions, complementary error function, which are tabulated or can be calculated numerically. Okay, so there's no analytical solution, but at least we have an expression that gives us the probability of error at the receiver, given a certain voltage, the threshold voltage. And this is an important point, because now we see that what we have is that the probability of error will depend on the value that we choose for the threshold voltage, and it will depend on the mean value and the amount of noise associated with each level. Okay. Now the question that we can ask now is the following. Given that we have a certain mean value for the on and off, a certain amount of noise at each level, what's the best threshold voltage that we can set at the receiver to minimize the probability of error? Because it's not straightforward to that what's the value that we should choose for the threshold voltage, right? For example, I think in certain limiting cases, we can understand that at least this is not for sure the best situation. Let's try to understand, to look for the solution like this. You see in this diagram here, this is the threshold voltage, okay? And now suppose that we can choose the threshold voltage, the value that exactly what we want. What values should we choose? Does anyone want to say something about this? Does anyone wants to make a guess, or
if their variances are equal, it should be right in between.
exactly. If the amount of noise here and here are the same, if this level here, right, are identical, then obviously I think it's more or less obvious that we should put the threshold level in between the two, right, at halfway. Okay, this is more or less intuitive. Because in the limiting cases, that's what I was going to discuss. If we place a threshold voltage very close to the on level, for example, obviously the threshold voltage is a long way from the zero level. And so when we transmit a zero, probably we have no errors at all because the threshold voltage is very far away from the off level. But then it's very close to the on level. And when we transmit ones, basically there will be a high probability that in some instances the noise comes below the threshold voltage, and there's certain probability that an error is detected, which can be quite high. So it's not really an optimum point to place the threshold voltage. And so if the noises are actually equal, we should put let's say the threshold voltage halfway between the on and the off. But as I said, usually in an optical communication system, sigma on is usually higher than sigma off, which means that this noise is a bit higher than this one. Then where should we place the threshold voltage?
Near the one with the smaller variance.
Exactly. We should, if the off has lower noise, then we should lower the threshold voltage as well. Okay, so there should be some mathematical way of expressing exactly what we mentioned right now, right? And there's a mathematical way of doing this. I'm going to do it in a slightly simple way than we did in fundamentals of telecommunications. I'm not going to make this very complex, but I think it's relatively easy to understand that basically we have this curve. Yes, we have this curve. Basically, we have to put the threshold voltage at the intersection of these two probability distribution functions. That's exactly what we said, right? And if the amount of noise is the same for both, then the width of the curves will be identical, and then the threshold voltage will be halfway. Okay, so relatively simply straightforward, which mathematically is equivalent of in these error functions with this argument. We can simply take the equality of both the arguments, which defines the optimum threshold voltage that gives us the optimum value to place the threshold voltage, and the final expression, if we solve this equation for the threshold voltage, then we have this equation here, okay, which is this one here. Which depends, as I said, on the amount of noise and the off and off levels, and on the and also on the mean values. Okay. For example, if from this expression, if sigma off equals sigma on, if you write this as sigma, then this equation gives us simply V on plus V off over 2, which is halfway mean value, right? Which was exactly what we would expect. And in that case, the probability of error, if you write Q as this variable here, which means in the equation that we had before, this is Q, but this was defined as identical, which is also Q, and then our equation becomes simply this one here. Okay, sorry, which is this value here. And so we have a simple expression that gives us the simple expression for the probability of error. And in this, the rest of the course, we're going to assume these simple conditions where we assume that we have optimum point for the threshold voltage, and the probability of error is going to be given by this expression here. Okay. Obviously, we see that there's a relation between the probability of error and this factor Q. And for the beta rate or probability of error of 10 to the minus 9, then Q is equal to 6. And this is a common value that we're going to use frequently in our analysis because the beta rate of 10 to the minus 9 is a typical standard value to assume for in telecommunications. Sometimes 10 to minus 12, if we're going to very high bit rates, then we need to increase the probability of decrease the beta rate to make sure not many errors are transmitted during a certain period of time. And this is a relation that given by that expression. So it's the probability of error to the Q. And we see that if Q is equal to 6, okay, this value here, then we have beta rate of 10 to the minus 9. Okay, so that's an important relation that we're going to use often. Okay. We're going to assume even, we know that in general, probability, the noise in the on level in optical communication system due to quantum noise is higher than the off level. But again, and in certain situations, we can approximate them as both being equal. And if that is the case, if the noise are identical, as shown here, okay, then I have already shown that, which is then the threshold voltage is halfway between the on and off level. Again, in addition, if we assume that off level corresponds to no light at all being transmitted, so 0 voltage, ideally, then in that case, the threshold voltage is simply the on level divided by 2, just halfway between the off and level. Okay, so quite simple result. The Q factor, assuming B off, and I'm going to write if we assume, so if you remember that Q factor is given by this expression here, or this one here. And so if B sorry, if B of is equal to 0, then Q will be the threshold voltage, which I will call it, it's V over, and if B on is equal to a certain voltage V, then the threshold voltage will be V over 2, and the Q factor is the threshold voltage, which is V over 2 sigma, where sigma equals sigma on equals sigma off. Okay, and that's what's done here in this equation. Sorry, I can't erase the traces there. And so Q factor is simply V, which is the V on divided by twice the standard deviation. But we know that V over sigma, so this is signal amplitude over noise amplitude. And so this is equal to the square root of the signal to noise ratio. And so we have here an important relation, which is that the Q factor inside the complementary error function is just 1/2 of the square root of the signal to noise ratio. And so if you remember, if we know the sources of noises at the receiver, we can determine the signal to noise ratio. Now, if we know the signal to noise ratio, we can determine the Q factor, and then from the Q factor, the probability of error, okay? Which is an important result, okay? And so we were able to establish a relation between the signal to noise ratio at the receiver and the probability of error, okay? Which is a very important result. Let's see if I can. So let's see if I can. Sorry, this some bug here. It doesn't do it. And this is remember that we've seen this plot of the probability of error as a function of Q. We can write a similar plot of the probability of error, but now as a function of V over sigma, which is the square root of the signal to noise ratio, okay, which is equivalent. Okay, let's see an example just to finish for today. If we have a bit error rate of 10 to the minus 9 as the bit error rate of 2 megabits per second, corresponding, for example, a telephone line, bit error rate of 10 to the minus 5 corresponds to 1 error in 100,000 bits transmitted. This is an error that occurs every 0.05 seconds. So to determine the, let's say, average time between consecutive errors, we need to take the number of transmitted bits without error divided by the transmission rate, which gives us 0.05 seconds, which obviously, for example, if you are on the telephone call and if every 50 milliseconds we have an error, this will obviously not be acceptable in a transmission. Even less if we are transmitting video of, for example, high quality video, for example, this is obviously not acceptable. But if we increase the bit error rate to 10 to the minus 9, this is equivalent to 1 error for every 8.3 minutes. And so for a telephone call, this probably will be quite acceptable. But even for higher bit rates, the bit error rate should even be lower, and sometimes it's chosen for very high bit rates at 10 to the minus 12. Okay. This is just so I think we are going to stop here and we leave this. And this is just an example of the procedure to calculate the signal to noise ratio. Just to complete this part, for example, for a bit error rate 10 to the minus 9, if you remember, we know that for bit error rate 10 to the minus 9, Q is equal to 6, right? And we know that Q is equal to V over twice sigma. And so we know that V over sigma equals 12, and V over sigma squared, which is 12 squared, which is 144, equals the signal to noise ratio. Okay. And so this bit error rate of 10 to the minus 9 is equivalent to a signal to noise ratio of 144 or 25.58 dB. Okay. Now, if we know, and we're going to see some examples in the next classes, some of the practical classes, if we know the signal to noise ratio that we need to obtain at the receiver for a bit error rate 10 to the minus 9, which is 144, and we know the sources of noise, the only thing we don't know is the signal level, which means we can actually calculate the signal level and determine the minimum signal power at the receiver or the receiver sensitivity to obtain that specific bit error rate. Okay, that's something we'll aim to do in a practical class as an example to show you how this works.